Speaking on their own.
Good
All right,
morning.
welcome. Yes, good morning, Victoria. And good morning, everyone.
Good morning.
Yes, I would want to welcome you to our fourth year presentations, final year project presentations. This is an exercise that we do on an annual basis. And today, I mean, we are quite grateful for this we are using a new license, a Zoom license that has been purchased by the MARM grant, which is a result of a collaboration that we are now having under the MARM program with the London Mathematical Society. In full, it's the Mentoring African Research in Mathematics. And we are quite happy that we have this collaboration that is started. And, so we have this Zoom license that will be an official license that we'll be using in our department and also to enhance that collaboration that we are currently having. So we also have our guest with us, Professor Leterio. And he's a key figure in this collaboration. So we will now commence these presentations, and I will hand this over to Vaino, Dr. Vaino Shaumbwa, to start the presentations. Thank you.
Thank you so much, Prof. And I also say the same. We are so grateful to the London Mathematical Society for this platform. It seems like we have a bit of a challenge here. The first presenter is not connected. Not sure if...
then we can move to the next one.
Yeah. The next one of the examiners not, maybe we can go to the third. Alfiko, do you think it will be, you'll be ready to take the first? The first what? Alfiko?
Yes, doctor.
Would you like to take the first part while Lakia is connecting?
Okay.
Yeah, no, it's not what you prepared for.
Just a moment, doctor.
Okay, just share your screen and Dr. Kamka and Dr. Skongo, are you ready for the assessment?
Yes, I'm ready.
Okay.
Yes, I'm ready.
Okay.
From Dr. Scott, I'm ready. Okay, thank you.
Alviku, it is 25 minutes and then 5 minutes for the questions.
Okay.
Yeah, you may just start as soon as your presentation is open. We are just waiting for you.
Can you hear me, doctor? Can you hear me?
Yes, we can hear you. Yeah.
All right. So respected lecturers and fellow students, good morning to you all. My name is Nankeni Haufiko, studying a Bachelor of Science in Mathematics Honors Computer Training. So my presentation is under the topic mathematical model for corruption management.
We can't see the presentation. Sorry, Haufiko.
Sorry?
We cannot see the presentation. Seems like you need to open it.
It's probably open, but it's not sharing the presentation, but rather sharing his screen.
Yeah, share the presentation, that screen.
Go back to share and then share the actual presentation. Yeah.
Yeah, we can see it now. Thank you.
So I chose this topic as corruption is ever present and performed in almost every country of the world, especially the developed. So firstly, let's have a look on what this project is all about. So in this paper, corruption is treated as an infection that spreads through social interaction. So a mathematical model for corruption dynamics is being developed and analyzed. So we are going to see this. Also the basic reproduction number that can be used to control the transmission dynamics of the diseases was obtained. So the analysis revealed that corruption endemic equilibrium state exists if R0 is greater than 1. So this R0 is a basic reproduction number. And also the result shows that the disease equilibrium is locally asymptotically stable if R0 is less than 1. Here are some keywords. So let's have a look at the table of contents. Firstly, I'm going to introduce the topic, and we'll have a look at the literature review, methodology, then we conclude. So, corruption represents a very dangerous social phenomenon being experienced in many parts of the world. So, corruption is generally defined as the misuse of public authority and has been a subject of substantial amount of empirical research over the past decades. So the first point here, it says that it has been variously defined as an illegal act that involves the abuse of public trust. It's according to these guys. In the words of transparency, corruption undermines good governance, it harms private sector and particularly hurts the poor. So it's also conventionally understood and referred to as a private work-taking behavior for someone who represents the state and as a public authority. So it is a symptom and a result of institutional weakness having negative effects on the economic performance of the country. So that's why it's a huge phenomenon with economic, political, social, and cultural dimensions which can be easily eliminated. So let's move to the program statement. Corruption is one of the biggest challenges of the contemporary world. Many countries around the globe suffer from deep-rooted corruption that hampers economic development and the damage social practices. I mean, justice. So It distorts the rule of law and weakens the institutional foundations on which growth depends. So, and that's why it's identified among the biggest obstacles to the economic and social development. So corruption has the most serious effect in developing countries. As a fact, as you can see in the presentation, like in Africa. Yeah, these are some of forms of corruption, like bribery, like fraud, extortion, and nepotism. There are a lot. Let's move to the objectives. So the study aims to review a mathematical model for modeling the spread and control of corruption. In doing so, we firstly aim to present an overview of the dynamics of transmissions of corruption. Secondly, to evaluate its effect on national development programs. And thirdly, to analyze the stability properties of the model, as well as quantity, as well as quantify the corruption-free equilibrium points. Another objective always is to prevent corruption and ethical practices. So the study will be useful in enriching national development plans of Namibia or any country of the world where as far as corruption management is concerned. And also to suggest the best strategies for controlling the spread of corruption in the society. It will also be vital in enforcing the anti-corruption laws. So systems dynamics model of corruption developed in this study would be of use to policy makers as well as non-governmental organizations to understand the complex nature of corruption. So corruption is elusive to define, but incredibly easy to recognize. So it's described as a complex and multifaceted phenomenon associated with all forms of human organization. So corruption degrades national security and international security. That's why it's a deep-rooted cause of instability and conflict, as it witnessed in the present situation. Now, due to this guy, which is indicated here, corruption could be characterized as a disease inherent to public power, an indication of bad governance. So the epidemiological corruption model was back reported by many authors, including Staterman, Becker, and many more. The authors study the effect of corruption on national development by modeling corruption as a disease. In particular, this guy here investigated an epidemiological corruption threshold based on the approximation of total population into three compartments: susceptible, corrupt, and honest, without giving stability analysis of the equilibrium point. However, the author didn't consider well the case of losing immunity of jailed corrupt that I'm going to show here. So let's move to the formulation of model. To formulate the model, the total population is divided into 5 compartments, namely susceptible, immune, corrupt, prosecuted, and removed, with the assumption that susceptible individuals are those who have never been engaged in any corrupt practices. Immune individuals, these are individuals that can never involve themselves in corrupt practice under any circumstances. Corrupt individuals are individuals who are often involved in corrupt practices, and these guys, they are capable of influencing susceptible individuals to become corrupt. Prosecuted individuals are those who have been convicted of corrupt practices and imprisoned for a specific period of time. The removed ones, these are ex-convicts who have been reformed while serving their jail terms and still can be influenced by the corrupt individuals. So the assumptions result in this system of nonlinear equations is equation 1. And here you can familiarize yourself with the parameters that are used here. So yeah, we have that all classes are subjected to a natural death at a rate mu. Now, solving the system in one, this system, it yields this solution that is represented by question 2, whereby Z1 to Z4 are given here. With S node, C node, V node, C node, and R node be initial conditions. Let's move to model analysis. Here we consider the region, this region, for the dynamics of equation 1. So, excuse me, just a moment. So let's consider the region, the dynamics of equation 1, whereby this dynamics can be studied in this region, and it can be shown that the region is positively invariant. So the rate of change of the total human total human population is then given by this equation. Now, applying the integrating factor method to equation 5, we get this equation 6. We have that this part is obtained by using the standard comparison theorem. So hence all the solutions enter this region and remain non-negative or non-negative initial conditions. So in this region, the model is well put mathematically and epidemiologically. So let's move to the corruption-free equilibrium. At the corruption-free equilibrium, the population-free, excuse me, Doctor, did you say something?
Please.
You may continue with the presentation.
At the corruption-free equilibrium, the population is free of corruption, so that only susceptible and immune individuals exist in the population. And it's given by this equation. Corruption endemic equilibrium. So the endemic equilibrium is the steady state solution of the corruption transmission model, where corruption persists in the population and all subpopulations are positive. The corruption endemic equilibrium then exists at this point. It is given as equation 10. Let's move to the basic reproduction number. So the basic reproduction number is a useful quantity in the epidemiology as it sets the threshold in the study of diseases, both for predicting its outbreak and for evaluating its control strategies. That's why we are going to consider it in this study. So now, using the next generation metric method is described in one. We have the matrices X sub I and V sub I for the new infection terms, and the remaining transfer terms are given, as you can see them here. And the basic reproduction number is obtained as follows. So this is what is considered as a next generation matrix method, and the characteristic equations becomes equation 16, whereby the spectral radius is given by this. So the spectral radius is just the same as the basic reproduction number. It's given by equation 17. Now let's move to the methodology part. So we are taking the existence of local stability of corruption-free equilibrium. We have a proposition. It says that the corruption-free equilibrium of the model is locally asymptotically stable if R0 is less than 1. So the Jacobian stability technique, which requires that all eigenvalues be negative for stability to hold, will be used to prove the existence of local stability of corruption-free equilibrium. So linearization of the model equations at equilibrium point, it gives this Jacobian matrix, and the characteristic equations are given by this, which gives I think there's something missing here. No, it just gives the product of all these values in the main diagonal, and they will be equal to 0, whereby the eigenvalues will lambda 1 will be equal to minus Z1 and lambda 2 will be minus U. I think it's clear. And I'm so sorry for this. So we have that if this part, if we make this part less than Z2, like this one, then if, let me see if I can write it clearly. Okay. And not, if we make this less than Z2, and we multiply both sides by Z2 and we get 1 here, then we get that our R naught will be less than 1. And we know, and we have that all the eigenvalues will be negative if R naught is below 1, and therefore the corruption-free endemic equilibrium is locally asymptotically stable if R naught is below 1. So, and that proves the proposition. So I'm so sorry, I don't know what happened here. Some things are missing now. So let's move to the existence of local stability of corruption endemic equilibrium. So the Jacobian stability technique will be used to prove the local stability of the corruption endemic equilibrium, and so the Jacobian stability technique will be used to prove the local stability of the corruption endemic equilibrium. And generalization of the model when gives this Jacobian matrix, whereby the characteristic equations of the triangular matrix given by this, whereby A, B, and E are given by Z. This is the eigenvalues are given by this point.
Ofiku?
So then we,
Ofiku, sorry, Ofiku, can you hear me?
yeah, I can hear you.
You have 5 minutes, please. You have 5 minutes remaining.
Okay. If R naught is greater than 1, then we conclude that the corruption endemic equilibrium state is locally asymptotically stable. So corruption challenge good governance and become a hinder for investment. Eliminating corruption will free significant resources for investment in infrastructures and in programs that deliver service to the poor. So interestingly, the negative impact of corruption on economic growth is largely identified in public procurement, as it affects life in many different ways. So, ladies and gentlemen, this is the end of my presentation. And here are my references.
Oh, okay, thank you. We have questions, comments. We have 5 minutes. And questions and comments. Anyone?
Yes, I wanted to ask a few questions and give some recommendations.
Okay, you may please go ahead.
Yes. On the system, on question 1, I wanted to know why is it just provided without initial conditions?
Where?
Your question 1. Why is it just presented without initial conditions?
Did you get the question?
Can you say that again, Doctor?
Maybe let me finish the question, then maybe you can answer, because maybe it seems network problem. The second question is the characteristic equation, the one which is expressed in terms of determinant, is also expressed as an expression. It's not an equation. And I wanted to know why is it like that? And my third question is, can you give us a practical example when you mean corruption is at equilibrium? And I will give my recommendation once I have the response. Thank you.
Over to you, Aufiku. Aufiku, are you there? Aufiku, are you there? Aufiku, time is, we only have 2 minutes remaining before we move to the next presenter.
Is he connected though?
Yes, he is.
He's still visible. His screen is shared.
Yeah, but why is
one wonders what is happening there?
or did he mute himself?
No, it's not muted.
You can go to the next presenter.
Go to the next presenter.
Okay.
All right.
Thank you. Rachel, are you ready?
Yeah. Yes, I'm here.
Okay. And Mr. VJ and Dr. Lodrick? Yes, okay. We are connected, that's fine. You may start, please.
Yes, good morning, everyone. My name is Rachel Ndongo. I will be presenting on longevity risk management and modeling using the Liketa model. My supervisor is Dr. Samuel Mulu. This is my presentation outline containing of 5 sections. Starting with longevity risk is a risk of people outliving their savings, basically. So it's a risk faced by pension funds, policyholders, individuals as well. This risk causes a negative impact on profit margins of insurance companies. Background of the study: longevity risk is one of the fast growing by day. It's one of the biggest frontiers that is still challenging the market. It was not as It was not as significant as it is today for a few decades back. Longevity risk has increased significantly due to medical developments and other sciences that help develop economies. Statement of the problem is that future developments in life expectancy are uncertain. It's not dependent on the past, neither the present. The future mortality trends are independent of what happens today. Objectives of my study are that we analyze longevity risk in its significance, design and explore development in longevity risk management and modeling. Significance of the study, with the constant improvements in longevity, it is significant that insurance funds and life insurance companies take into consideration longevity risk and look into new developments when it comes to managing and modeling this risk. We're moving on to the longevity risk management. In this, we present a few. I will take out the buy-ins and the buyouts under the insurance hedging solution, also known as natural hedging solutions. Buy-ins and buyouts are basically the risk transfer transactions, commonly known as bulk annuities. Bulk annuities are insurance contracts where the pension funds transfers all the risk that is associated with longevity to a protection seller, to another insurance company. Starting with the buyout is a transaction of risk transfer where pension funds, assets, and liabilities are transferred to a risk protection seller in return for an upfront payment, whereas in a buy-in is similar to a buyout, but the difference is that it does not transfer all its liabilities. The key difference between the buy-in and the buyout are explained by the involved credit risk, which we can show in the risk premium calculations. So the buyout buyer transfers all risk that is associated with longevity. It transfers the investment risk plus the longevity risk as well. Whereas a buy-in, because they don't transfer all its liabilities, they still bear the default risk of the premium of the protection seller. And moving on to capital market solutions, in this section we also present a few market solutions. The Q forward, starting with Q forward, letter Q in actuarial sciences presents mortality. So a Q forward is a mortality forward contract. This is an agreement between two parties to exchange the future date and amount proportional to the realized mortality rate of a given population in return for an amount proportional to fixed mortality rate that has been mutually agreed on at the inception of the contract. The significance of Q forwards is that it can be used to hedge other longevity instruments in the capital market. This is an example of a Q forward contract used. This is an example of a Q forward contract used for hedging a longevity swap. This is the survival rate. We use a fixed interest rate to show how a Q forward, a mortality forward contract can be used to hedge a longevity swap. Whereas we have the Q forward mortality rate